confirming. And thank you so much, everyone, for taking your time and joining us on this live session by Manifold AI Learning. So, this session is made possible with the help of the team from Manifold AI Learning. So, Mindful AI Learning is an online academy which with the goal to empower the learners with the knowledge and the skill sets which can be directly applied to solving the real world problems in data science, machine learning, and artificial intelligence. And for those of you who do not know do not know me, my name is Nachiket Murthy. I'm one of the instructor at Manifold AI Learning, where I take up the sessions related to machine learning, data science, deep learning, and the ML Ops, generative AI. So these are the topics which I'm currently taking in with the Manifold AI Learning, and I have authored multiple courses with Manifold AI Learning. So it has been a pleasure to interact with each and every one of you today. Now, first of all, let's understand why this session is important for you. So one of the common thing that I would face, I mean, as a learner that I have faced was when I was reading any topic. So if there was a batch or uh, if there was a set of learners who are learning the same resources as me, then I would have definitely made a lot of progress because sometimes what used to happen for me in general was like whenever I was taking up any new learning activity, first of all, there was a resistance in my so in like there was a resistance in me which was causing me not to progress as I would expect. So in such scenarios, one thing that has helped me was like there were two, three friends who are having and who are in a same mindset as me at that time. So who are all in touch with me and I still discuss with them. So what was helping me was like my close friends who are in the same mindset as me and who are actually referring to the same resources. So we started discussing about the topics that we have learned this week. So even though I might have missed or one or two topics which I couldn't follow, when I started interacting with them, I started gaining more confidence as, okay, hey, it's actually easy and I can easily do it. Now, that is a feeling that I was actually getting it every time that I was interacting with my friends. Now, I wanted to give the same experience for the learners of our platform, that is this Manifold AI Learning. So, one of the book that I have recently come across, and actually I've referred it multiple times and I've spoken about it, that's the hands-on machine learning. Now, I found that there are multiple learners like me who are stuck in this learning journey. So, I wanted to make it simple for you so that to summarize what is happening over there, give you a gist about the important topics that you need to know from the machine learning so that you can progress in your learning journey. Okay, so that's the overall idea, guys. And thank you again for folks who have joined with us from various time zone and interacting with us. So, like, if you have got any feedback, please feel free to let us know in the Q&A or in the chat window. We'll be happy to help you, and I'll ensure that your feedbacks are received and we'll be incorporating in the further sessions. Now, the agenda of today's session is to discuss about one of the powerful algorithm in machine learning, that is support vector machine. Now, if you're someone who's in getting started in machine learning, or even if you're someone who has experienced in support vector machine, so I would highly recommend you to stay with us till the end because I'll be taking you through some of the important concepts that you need to know. So we'll not go dive into we'll not getting stuck inside the technical part, but what we try to do is we try to build the high level intuition about this support vector machine. So by the end of this session, you will be confident as which algorithm to choose. Like for example, if we take up the support vector machine itself, you will be confident as when you will be preferring the support vector machine and what are the downsides about it. So that would be the overall agenda of this session. So I hope we are good to start, guys. So team, if you are good to start, please confirm by typing as all good to confirm that we are good to start in today's session. Thank you, Daiksha. Thank you, Samiksha. Thank you, Sridhar. Thank you, Samyukta. Thank you, Maheshwaran. Thank you, Soundarya. Okay. How about others? Okay. Thank you so much, team. Okay, I see a lot of thumbs up that is coming in. Thank you, folks, for interacting and confirming through the chat window as well as your emojis. So, folks who have not joined with us on the webinar link, so let me share the webinar link in the social media platform so that you can join the webinar link. So, at the end of the session, in case if you have got any specific question, you can feel free to join that webinar link and you can actually interact with me by unmuting yourself in case if you have joined through our social media platforms. I've just shared the link over here in the live chat, especially on the social media platform. You can join in through that link and you can interact with me. Okay, guys. So the agenda of today's session is to discuss about the support vector machine. So as I mentioned, this session is made possible with the help of the Manifold AI Learning team, and I've got a chance to author multiple courses with them. And one such course that I want to bring to your notice before we proceed ahead, so is the course on generative AI. Now, these days, we see a lot of demand, especially in this domain of generative AI. Now, to help the learners to master this generative AI and to progress in a sequential way, there has been a package that has been created by the Manifold AI Learning. Now, this package is consisting of more than 10 courses to help you begin your generative AI journey in a sequential way. Now, this package is consisting of Python, the NLP, the prompt engineering with LLM ops, the AWS certified machine learning, deep learning with TensorFlow, PyTorch, linear algebra, statistics, calculus, and even you've got the new course that is coming in. There's an upcoming course on Python programming for DevOps. Even this is part of the package that is the generative AI mastery package. I highly recommend you to check out. There's a offer that is running in the Manifold AI Learning site, so which is Holy. You can actually get 15% off. And remember, this offer is valid for next 24 hours. I think by the end of today, IST time, the offer gets expired. So ensure you check out the course and register over here, and so that you can progress in your generative AI learning journey. So you can check out the website and you can reach out to the support team over here for any help. So I look forward to seeing you on the session, guys. So you can check out the course details. As I mentioned, it contains everything. So it's a package which is worth of more than $3,000 has been compressed and created as a package so that you get the value for money in your learning journey. Okay, now let's come back to our agenda and let's proceed ahead and uh, look into our today's session agenda, which is about the support vector machine. Now, in order for you to proceed ahead and learn more about the support vector machine, I've created some slide. First, we'll go through the same. I'll tell you at a very high level what exactly is a support vector machine in a simplistic manner. From there, we would go ahead and build our intuition. Okay, so that's the approach, the same approach that we have taken till now. That's the same approach that I'll be taking in today's session as well. Now, when we talk about this support vector machine, so support vector machine, if you're someone who have worked and learned about the deep learning or in research paper, so this support vector machine has been considered one of the top algorithm, especially in the olden days. The reason because it has got the flexibility and it has got the power to learn the patterns in complex data set. And that's the importance of this support vector machine. And if I want to give you a high level idea about this support vector machine algorithm, it's an algorithm where we plot each data item as a point in n dimensional space. Now, how do you describe the number of dimension? It's nothing but the number of features in your given data set. To make it simple, suppose if you have the columns like loan amount, loan tenure, maybe salary, and then you have a column which says that whether to approve the loan or not. I'll say status. So let's assume these are three features, x1, x2, x3, and this is your target y. Now, when you have such scenario, let's say three features x1, x2, x3, and you have a target that is y, in such scenarios, I would say that, okay, okay, I apologize, guys. Okay, so I hope it's visible. Thank you so much, Shankar, for letting me know. Okay, so is it visible now, team? Shankar, Piyush. Okay, thank you so much, guys. Okay, all right. All right. So when we have three features x1, x2, x3, and the target variable y, so this is a scenario where I've got three features and one target. Now, when I have this example, okay, if I take up this example, this is an example. I've got three features and one target. Now, what we are saying is, in the case of support vector machine, we are going to plot each and every data point. Now, what is a data point? To put it simply, each and every row in the data set is treated as a data point. So we are saying that we plot each row in the given data set as a point in n-dimensional space. In this scenario, since I have three features, I'll be plotting it in three-dimensional space, okay, where each feature being the value in that particular coordinate. That means in my x-axis, I'll have x1, which is loan amount. In my y-axis, maybe I'll have x2, which I'll call it as loan tenure. And in my z-axis, that is my feature x3, which is my salary. And I'll be drawing a plot. I'll be representing each and every row as a data point. Then once I represent each and every row in my data set as a data point, then what we'll be doing? We would go ahead and classify such collection of data points into classes by drawing a decision boundary. And we call this decision boundary as a hyperplane. So this is the hyperplane which separates these points. Okay, you will plot each and every data point and you will, and obviously this green and red is basically from your training data only. Okay, so these are basically the training data only. Now you'll draw a hyperplane. Okay, you'll draw a hyperplane, and this hyperplane is the one that differentiates between two classes that we have got in this example. So that's the intuition of this support vector machine algorithm. We are basically trying to draw a hyperplane which separates the data points. Clearly, this is an example of the classification. That's what we'll be using in most of the scenarios. Now, here you might be wondering as when I have this set of data points, let's assume if you take up this slide over here, so we can see that over here in this slide, I've got the collection of data points with me. Now for this collection of data points, which is over here, now the question is, how do I go ahead and draw that hyperplane, which is a best possible hyperplane? So that's the question that we'll have by looking at our previous explanation. So let us try to understand that part and uncover it to understand how do we actually draw this hyperplane which separates the data points. Well, the way that we draw it is we'll try to go ahead and draw the straight lines which separates the data points. Okay, so obviously by comparing to my previous slide to my current slide, so here in this slide, I've drawn the lines which was able to separate my red data points, that is red circle, with blue stars. Now I'm able to classify the given examples. But now we have arrived at another problem. The another problem is which hyperplane should I use? Like, should I choose A or should I choose B or should I choose C? Now that's a question that we have got. So we have solved one problem, that is deciding as how to decide a hyperplane or how to draw a hyperplane. Now once I've drawn the hyperplane, there are multiple ways of drawing that hyperplane. So in such scenarios, now I've got three hyperplane A, B and C. Now the question is, which one should I use? Well, we are going to choose a hyperplane such that the hyperplane is at the hyperplane is such a way that it is at the maximum distance possible from both the classes. So that is how we'll be choosing a hyperplane. We'll choose a hyperplane such that the hyperplane line that we have got, it is equidistant from the data points of both the classes. So that is the overall way in which we would go ahead and draw the hyperplane. Now, the question that we would get is, okay, this is a happy path. So I've got all the data points belong to the same class. Now, what happens when we have a tricky scenario as like this? Like when I have got the data points where there are some blue data points in the red region. Now, in such scenarios, how do we go about and draw the hyperplane? Well, in this scenario, we will make use of various hyperparameters that we have got in support vector machine so that we can allow the misclassification for the given data. Okay, that's the overall high level intuition behind this support vector machine. So to summarize it, when we say support vector machine, it's an algorithm which separates the data points by drawing a hyperplane. Now, hyperplane is a straight line which classifies the given data into like into two classes, which separates the data points into two examples. Assuming it's a binary classification, which classifies the data points into two classes, it separates it. Okay, now the way that we draw this hyperplane is we'll draw a hyperplane such that it separates the data as much as possible. That means it is at the equidistant from both the classes. And I have already mentioned that if I have any data which is not perfect in such scenarios, we have some hyperparameters so that we can tune it. We can actually tune the hyperparameters and separate the data points. So this is the learning journey that we had just now to get a high level idea about this support vector machine. Now, when we are trying to define this hyperplane, when we are trying to define this hyperplane, so I can draw a hyperplane which separates the data point with various ways. And these ways are defined by kernels of the support vector machine. In support vector machine, we basically have three kernels: linear kernel, polynomial kernel, and the another one is called as, let's see, yeah, it's called as radial basis kernel, or RBF, radial basis function kernel. So these are the types of kernel that are available, using which we can go ahead and separate the data points in terms of the like by drawing a hyperplane. Okay, so that's the overall idea right here, team. So you'll be able to uh, have these kernels, linear, polynomial, and Gaussian RBF, and using such kernel, we'll be able to separate the data points. Okay, now let us understand what are these kernels and what is its role at a very high level. Now, when we talk about the kernels, so here we've got a linear kernel. Now, if I'm making use of a linear kernel, then in such scenario, I'll be separating the data points with the hyperplane which follows the equation, which is the straight line function. So I'm trying to establish a linear relationship and I'll try to draw a straight line which separates the given data points into the classes. That's called as a linear kernel. And we have a polynomial kernel. Now this polynomial kernel, what it does in the backend is on the data set, first it will generate polynomial features. It will generate the polynomial features, and once it generates the polynomial features, on top of that, obviously when you have the polynomial features data, so on top of that it will apply some kind of a linear kernel. So obviously it means that we are applying some kind of a polynomial regression. That's what happens in the polynomial regression, and that is what would happen in case of polynomial degree as well, that is polynomial kernel as well. So here we'll define the degree d for the polynomial, and we'll have to specify whenever we are applying this support vector machine if I'm using the polynomial kernel. And the other type of kernel that we have got is the radial basis kernel. Now here in the case of this radial basis kernel, we have a radial basis function. So using the radial basis function, we will transform our data first. We will transform our existing data. Now, once we transform the existing data, then on top of that, we would go ahead and draw the line or addition boundary which separates the data point. So that's the intuition behind this radial basis function kernel. Here, there are various parameters We have got a gamma as a parameter which ranges between 0 to 1. So what it means is this gamma is a hyperparameter. We'll have to tune it when we are choosing the radial basis kernel. And what it says is a higher value of gamma will perfectly fit the training data set, which might cause the overfitting. And when I have gamma as 0.1, it is considered to be a good default value. So since it's a value that we have to specify during the training, we call this as a one of the hyperparameter of the support vector machine. Now, in this support vector machine algorithm, guys, so we have now learned about the three kernels, isn't it? Now you might be wondering, when do I use what? Well, let me just give you one more illustration to help you understand when do you choose which kernel. Now, if you consider the example that you see right now, so this is a case where I have blue data points in the middle and I have the surrounding red data points. Now, in this case, when I have blue data points in the middle and surrounding red data points, here, no matter how I draw a straight line, I cannot classify the data points. See, you can observe here on my screen, no matter how I draw, I cannot separate the data points with the help of this decision boundary or hyperplane. So obviously, it means that I cannot apply the linear kernel. Now, what we do in such scenarios is we will either go for the polynomial kernel or the Gaussian RBF kernel. To illustrate this, let me take you over here. See, what we have done is we have performed some kind of transformation, assuming it's a polynomial transformation, or it can be a transformation with the help of the Gaussian RBF kernel. Now, as a result of this, there's a new dimension that has been generated from the existing data points of x1 and x2. Now, once I have generated the new feature that I'm calling it as Z, now I'm able to separate the data points. So this is just a 2D view of what we have seen earlier. Now, if I want to give you a 3D visualization, so this is how it would actually look like. So here I'll be adding a third dimension, which is going to add a height, okay, which is going to add a height that you see right here. Now, as a result of this, so think of it in this way, like there is x1, there is somewhere x2 like this, and here the top that you see, this is z. So since we are adding the z, which is a new dimension, so I'm now able to separate the data points by drawing the hyperplane right now. So if I want to give you in an animated way, think of it in this way. So you've got a 2D plane where you have all the data points. Now on this 2D plane, what you will do is you will perform the transformation and you will add a height like this, which will become some kind of a parabola as a result of adding the height. Now in this parabola, you would go ahead and fit in your kernel and try to separate the data points. So that's the intuition of applying the SVM on the complex data set. We would go ahead and perform the transform on the existing data. Then we'll draw the hyperplane to separate the data points. So that's a very high level intuition behind this support vector machines. All right, guys. So I'll take a pause here, guys. So do you have any question on the topics that we have just discussed? So we just discussed about the support vector machine and its intuition. So let me know, folks, if you have got any question. If you're clear, please confirm by typing as all good. I see a few questions I'll be answering just now. Yeah, like others, if you have got any question, please feel free to let me know now. If you're clear, please confirm by typing as all good. Okay, thank you, Prakash. Prakash, thank you, Prashant. Thank you, Krish. Thank you, Sangeeta. Thank you, Dheeraj. Okay, so okay, there's a question from learner. Okay, success Ekoshki says, is this recorded? Yes, Ekosuhi. Yeah, this session is getting recorded. I'll be sharing at the end as how to access the session recording. And there's a question over here from Shankar. Shankar says that what is linear and non-linear data? That's a good question, Shankar. So when I say linear data, it's like I'll call it as a data, which is a linear one, where I can separate the two set of classes with a straight line. So that's what I would call it as a linear data. I mean, where it is a linearly separable data. Okay, and when I say non-linear data, it's a kind of a data where I cannot draw a straight line which separates those classes. So that's called as a nonlinear data. Okay. And another question that I see right here is Piyush, example that you have shown is classification problem, right? So how does the support vector look like for regression problem? So in the case of regression, so what we are actually trying to do is, so we would go ahead and if I'm making use of a linear kernel, think of it that it is very much similar to the linear regression algorithm that you have got because you're trying to draw a straight line which predicts the data points. Depending on the type of kernel, the transformations will be performed on the data set and then you will go ahead and predict the output. So that's the idea and the intuition behind the regression. Okay, thank you, Ambuj. Okay, I see Shankar has raised the hand. So Shankar, is your question answered? Is it the same? Okay, sure, Shankar, definitely. Okay, so the question that I've got is, can you brief again on hyperplane on nonlinear data? That's a good one. Okay, so here, let me just give you an example. Okay, let's say that I've got two features, x1 and x2. Okay, so I'll take up some dummy values. Let's say 2, 4, 2, 3, 5, 6, 1, 7, and 8. Now, assuming that these are the data points and I have got some y, 0, 0, 1, 1, and something. Let's assume this is what it says. 4, 2 is some one data point and 3, 5 is another data point and 6, 1 is one data point and 7, 8 is another data point. Let's say these are the two different data point that I've got. Okay, and so here, what we are trying to say is when we are when we have such data points, what we will do is we'll perform the transformation, assuming that I have the data points. This cannot be like fit with the help of the linear hyperplane. So what I'll do is I'll perform the transformation. So I'll apply the polynomial transforms. Like for example, I'll just say z is equal to x1 square plus x2 square. I'm just coming up with some random formula just to give you the illustration behind it. So think of it, this is one of the transformation that I'm doing it on the existing features. So x1 square plus x2 square, that is 4 square plus 2 square. So 16 plus 4, 20. 9 plus 25 is 34, 36 plus 1 is 37, 49 plus 64 maybe 113. So this is what the Z would get. Now, instead of representing my data point in two dimension, now what I'll do is I'll try to represent it in three dimension x1, x2, and z, where one data point over here, this represents a data point of 4, 2, 20, and the next data point over here, 3, 5, 34 will be represented as another data point in three-dimension plane, 6, 1, 37 will be represented in another data point in three-dimension plane, and that's how I would go ahead and represent it in the higher level dimension after the transformation. So here in this example, I've just shown you some dummy example as x1 square plus x2, but when you apply the polynomial transforms, it generates as it depends on the number of features. It will generate x square and 1 x and x square. Along with that, it will also consider x1 square, x2 square something. Okay, but it will generate multiple features and will use that updated data to learn the relationship. Now, once I draw it in multiple dimension, then I would go ahead and draw a data plane which separates the data points. Okay, is it clear now, Shankar? Now, how about others? Any other questions, team? Okay, thank you, team, for confirming. Perfect, guys. So let's proceed ahead in the learning journey. So what you have learned is you have got the high level intuition. Okay, you now have the high level intuition behind our support vector machine. Like this is another example which gives you the intuition as well. Let me come back. See, I've got the data point. So maybe I've added one more dimension as Z. Now, as a result of adding the Z, you can see there is a hyperplane which separates the data points. So in two dimension, it was not possible. After adding a third dimension, that means after the transformation, so I'm able to separate the data points with the help of a hyperplane. So that's the overall idea about this support vector machines, guys. Okay, so now that this concept is clear, so let's take up an hands-on activity which helps us to build the intuition behind the support vector machine and how we can implement it in a hands-on manner. Okay, so let's go ahead and do that. I'm trying to get my notebook so that I can walk you through some examples as well. Okay, I found a notebook. Let me share you the screen again. Okay, so this is a notebook that I've prepared using the hands-on machine learning, and I've simplified it so that we get a better understanding, guys. Okay, so here in this notebook, so what we'll do is we'll start by loading the necessary libraries. So here I'm loading the NumPy, Pandas, Matplotlib, and for the demonstration, I'm making use of the iris data set that we have got. Okay, so we'll make use of this iris data set. And here, once I've done, so just for our help on the intuition, so what we are going to choose is we'll make use of the uh, like the task of binary classification. Okay, we'll perform the binary classification on this given data set, and we would go ahead and try to build the intuition. See, in this given example, this is how my data set would look like. This data point belongs to one class, and this data point belongs to another class. So this is how our data set would look like. Now, once, as you can clearly see, this is the kind of data which we can separate the data points in a linear manner. That means even if I make use of the linear kernel, I will be able to go ahead and separate these data points in an efficient way. That's what I can do it. So now that we can see that, okay, we can go ahead and separate the data points. What we'll be doing here, I've imported the support vector machine algorithm. So to import it, it's sklearn.svm. We have imported the SVC, that is support vector classifier. Okay, now once we have imported it, so we'll have to specify the hyperparameter. I'll mention the kernel as linear and followed by the value C as 999. So C is one of the hyperparameter that we have got, especially while using the linear kernel. So when I set the value of C to a maximum value, so at that time, it will be a hard classifier. That means it will not tolerate any misclassifications of the given data. So we'll instantiate the model with the large value of C, and then we'll perform the fit on this given data set. Now, once the fit has been completed, so it basically draws us hyperplane which separates both the data points, and this will be a hyperplane. Now, apart from this hyperplane, there are two things that we'll also identify. They are actually called as support vectors. So support vectors are basically those data points. Okay, support vectors are basically those data points which are nearest to my hyperplane. That's what we call it as a support vectors. Now, once I perform the fit on this given data set, so it will help me to find the values of this coefficient, that is the coefficient of drawing this linear regression line, and the intercept term. So using this coefficient and the intercept, we can go ahead and create a decision boundary. So there's a function that has been created. It's a custom function. What we did is we went ahead and created this function, which will help us to draw the hyperplane so that we get a visualization as how it actually works. So I'll draw a decision boundary, and once I specify my model and mention some random data, we can see that, see, the data points which are closer to my hyperplane are basically the support vectors that you see here in this diagram. Okay, so these are the support vectors. And the middle line that you see, that's the hyperplane that we have found for this given data set, which separates the data points. So that's what it is happening right here, team. Ahead. So we have looked into the support vectors, and now when we talk about the support vector machine, so one thing that you need to do is you need to go ahead and perform the standard scaler. So application of scaling is very much important when we talk about application of support vectors. Now to give you an illustration, just observe the plot that you see right here. See, if this is a data on the original data, you can see that on the unscaled data, okay, on the unscaled data, you can see that there's no way to separate the data, like the data points are much closer to the hyperplane, but on the scale data you can separate it in an effective manner. Okay, that's something that you need to remember when we talk about scaling the data for the support vectors. And we can also apply the SVM to the non-linear data as well. So there are the additional code that has been written over here to explain about the non-linear kernel and how to apply it on the data set. So what we'll be doing is, since it requires a separate explanation and also explanation about some of the important things which is related to the scale and pipeline and everything. So what I'll be doing is I'll be sharing you this code in the notebook. So uh, I'll be sharing it on our platform itself. So if you go to the manifoldlearning.com, select the courses. So click on this hands-on machine learning. So from this hands-on machine learning, so I'll be attaching the today's session as well as the notes. So let me just upload the notebook right away so that you can actually download it. So I would go ahead and upload it under this chapter 5. So we'll be attaching our today's session recording here once the webinar is completed. For now, I would go ahead and upload the notebook, the Python notebook. So go ahead and access the code over here by referring over here in the chat window or in the or from the chat window so that you can access the source code, guys. Okay, let me do it right away. So this is where you can access the source code. Use the link and access the source code, and the sessions recording will also be made available in this portal itself. You can just access the learning content now, and then you can access the sessions recording and also the source code. And I'll also attach this slides as well for your reference so that you can keep it. So what we have learned as part of your today's learning journey is we have learned about the support vector machine, the intuition behind it, the various kernels of the support vector machine, and also the implementation. Now, as we progress in the next session, we will explore the other kernels that we have got, that is polynomial kernel and Gaussian radial basis kernel. And there I'll take you through some of the important topics such as application of pipeline and working with the same. Okay, so folks, there are some questions over here. So let me just answer those. And if you have got any other questions, please feel free to let me know, team. Okay, now one question that I've got is from Piyush. So the question from Piyush says that is there any concept of multiple hyperplane? So Piyush, in such scenarios, we have two options. Like we can actually use this binary for multi-class classification. The technique that we'll be using is one versus one or one versus rest. So maybe I can touch base more on the next session because that requires some additional explanation. I'll definitely explain, take it up in the next session. Okay, and when we talk about the hyperplane, there is only two, since we have got two features, so only we'll have like two classes. So that's the reason we have only two support vectors. Okay, so I hope that answers your question as well, Shankar. All right, team. Now, as I mentioned earlier, so this session was made possible with the team of Manifold AI Learning. So do check out the course of generative AI and make the most of your learning journey and ensure that you get your skills, you get yourself upskilled in this most in-demand domain that is generative AI and the large language model operation that is LLM ops. I've shared you the links over here in the chat window, and I've shared you the link to access the session's recording as well as the course content, guys. That is this hands-on machine learning, the recording as well. So again, guys, thank you so much again for joining in on this learning session. Now, I'll be here to answer any of the specific queries that you might have, and I look forward to seeing you on our next webinar session. Follow the Manifold AI Learning on LinkedIn and YouTube so that you can stay connected and you can be with us and be with us in all the upcoming learning journey too. Okay, so thank you, Piyush, and thank you, Rishikesh. Thank you, Samyukta. So thank you so much, guys, for being so interactive in this session. So, folks, if anyone has got any question, please feel free to let me know. If I missed your question, so please let me know too. So maybe let me know again. If you want me to unmute you, do let me know in the chat window so that I can unmute you in case if you prefer to speak. Okay, thank you, Srinivas. Thank you, Kant. Thank you, Krishna. Thank you, Bhavna. Okay, thank you so much, everyone. And it was great to interact with each and every one of you. And I hope to see you next time.